All right, are we ready? Lindsay, here we go. All right, it says, is this not what you guys, oh no, you got it. Okay, you're good. What? We're turning in the homework, but we're going to go over it first. Okay, Matthew, here we go. Number one says we are going to compare and contrast linear and exponential functions. So let's go linear, and let's go exponential. This is the homework, and let's each, well, I mean, technically it was from Wednesday. I was gone yesterday. I was at a math. Yeah, that's called lunch. That's not called skipping. Um, what's that? I don't know what you're talking about. I went and had lunch. Yep. Oh, I see. No, I was in a math meeting all day yesterday. All the math teachers were gone. Did you not notice that Miss McElliott had a sub and Mr. Bates? I guess you guys are only in one math class. It was pretty boring. We were looking at some new curriculum. The books that we have right now are like 10 years old, and so we're going to get some new books. But there's a process that you have to go through to check and make sure that they fit all the different things. So yeah, it was. What's that? I'm a little worried about the new ones that we looked at yesterday because it's like this huge book of what do they call consumables? So the key like write in them. So they're paper. They're not like a textbook. Yeah. So we kind of talked about like how could you do that as if it's this huge book, and then if you take it and you leave it in the back of your truck and it gets all wet, then it's ruined. So we talked about giving you guys you'll be gone, but binders, and then just doing like a chapter at a time. But then you have to tear them all. I don't know. Yeah. It's different. It's different. They teach math a little bit. They want us to teach math a little bit differently now. But whatever. It's all math. It's fine. I could have just looked at it for an hour and gone, yeah, it's good. But we had to. Okay. Did I pick someone? Nathan. Tell me something that's either different or the same about linear and exponential functions. Just one thing. Anything that's different or the same about exponential functions. How about if Talia gets us started? Maybe that'll jog your brain a little bit. Linear is always continuous, and exponential functions are continuous as well. So we could go continuous and continuous. All right, nice job. Way to throw out a big old vocabulary word. I guess you said connected, I said continuous. But okay, Matthew, something that's the same or different about linear and exponential functions. What's that? Okay. Nice. It was, huh? Okay, so they can have different y-intercepts. Sure, they could start at a different place. That works. Okay. Yeah, something that's the same or different about linear and exponential functions? What you got? They have, okay, yeah, exponential a lot of times don't have an x-intercept. Yeah, so exponential sometimes doesn't have an x-intercept. Yeah, absolutely. Right, no, get us thinking about x-intercepts. Okay, Talia, what about you? Both are, what? Oh, you have a thing Alexa, you have a thing? Lindsay, you guys are working on a thing right now? Okay. I'm sorry, what? Okay, are they always increasing? Can you draw a line that's going down instead of up? Okay. Can you draw an exponential function that's going down? Okay. So they can both. So they could both increase or decrease. Okay. Riley? Same or different about linear and exponential functions? What's that? 4. What's the same or what's different about linear and exponential functions? Okay, yeah, that's what Talia was talking about. They both can increase or decrease. Is there a difference in the way that they go up? Okay, good. So linear increases or decreases at the same rate, whereas an exponential function gets steeper. Okay, the slope of an exponential function changes. The slope of a linear function is the same the whole time. Okay, nice job, Riley. Well, you said something that nobody has stolen from you yet. I have not yet written it down. McKenna? Right, so we kind of did that here. It sometimes doesn't have an x-intercept. Okay, what's that? That's all you got. Okay. Luis? Okay, good. Linear functions are straight. And these are girls. Can you tone it down just a little bit? Thank you. Exponential functions are curved, okay? And that is why linear functions always increase or decrease at the same rate, whereas exponential functions, the rate of change changes. Okay, good. This is made from adding or subtracting, and then this one is made from multiplying. All right? Now I feel like we're good, Nathan. Okay? All right, number 2 and 3. Okay, for each graph, so we're back to this. Identify the domain, range, increasing, decreasing, and let's use ourselves some interval notation. So, Luis, you want to get us started? What's the domain of this guy here? Okay, good. And the -5 gets a square bracket, and the 2 gets a round bracket because it never actually gets to 2. Okay. How about the range? How about the y values? Awesome. Okay. So the domain is the x's. That goes from -5 to 2. The range is the y's. That goes from -6 to 5. And that point isn't actually on the graph, so it always gets a round bracket. Talia? Yeah, so here's how you get the domain and range, okay? Hang on just a sec, Jaron. Let's say this is a top view of your front yard, okay? And you know that under your front yard there is a metal sculpture buried somewhere, okay? You want to find it, but you don't want to dig up your whole yard. So you rent a metal detector and you start moving across your yard, okay? When you are moving from left to right, where does the metal detector first go off? At -5. And then as you continue to move from your left to the right, where does the metal detector stop? 2. So that's the domain. Okay? The range is doing the same thing, but you're now moving your metal detector up instead of across. Yep. Yep. Okay, does that help? Yeah, I know. Domain and range are a little bit tricky. Jaron? Okay, so the square bracket is if the graph actually has that point on the graph, and the round bracket is if that point isn't on the graph. And so since this is an empty circle, that means that that point's not actually on the graph. Okay, so then we also wanted to talk about increasing or decreasing. Yeah. So thanks. Dylan, where is this graph going up as you move from left to right? So we're going this way. Right, because it's never increasing, okay? So it's never going up, and then where is it going down? From what x values? -5 to 2. Because we're still doing the... Okay, when you're doing increasing and decreasing, it's kind of confusing because you're using both. You're looking at where the graph is going up or down to find the answer, but the answer that you give is the x's. Okay? Okay. Okay, they want you to state like where, oh, I guess it does say whether or not the function is increasing or decreasing, so you're probably right. So all we had to do for this was just maybe put increasing. Okay. You're right, I tried to make it too complicated. Okay, so let's take a look at another graph of a function. Weston, can you hit me with some domain and range on this guy? -3 and 2. Not feeling that. So again, let's go, this graph goes forever this way, right? So that's going to be -infinity. And then where does it stop? Right around what? Yeah, and so when we're doing domain, we only want the, let's go ahead and label that point since you said it. When we're doing domain, we only want the x values of that. Okay, so it's going to be -infinity to 4. Okay? Yeah. You always go left to right, yeah. Kind of. Yeah. Yeah. I don't want to say yes because we're about to do the range and this has an arrow and it's not going to be like that for the range. Weston, how low does this graph go? Okay, so this time I'm going to start at -6, but then how high does the graph go? Well, that's what Talia was just saying because of the arrow, but can you kind of see that it's leveling? But I want the y value now for range. So what's the y value that that's leveling out at? Yeah. Good. So the range is from -6 to -1. Okay? Okay? Jaren, is this graph increasing or decreasing as you go from left to right? What? I can hear him, sorry. Yeah, decreasing. And we're always going from left to right. Even though the arrow is pointing the other way, this case, we're going from left to right, so that's decreasing, okay? Alexa, I'm losing confidence that you're actually doing what you're supposed to do. I'm losing confidence that this plan is working for you. Okay, you guys should be doing, I mean, we're doing 3.4, so you guys should be up to 3.3 by now. Nathan, let's take a look at this one. What is the domain of this? So remember the domain is... Uh-huh. Okay, good. So -infinity to infinity. Now you might wonder, does this sort of like flatten out and never get to -7 or something? But we don't really know. And so you just get to decide, and that's what you decided. So we'll just call it good. What's the range? How low does it go? Uh-huh. 4. You're going to go curved on the 4. Can get close there, but not actually hit it. Okay, I would agree with you there. All right, and then what is that graph increasing or decreasing? Oh, no, not Alexa.
Alexa, is it increasing or decreasing?
Luis, is this graph as we go from left to yeah, increasing? Okay. Pretty straightforward, yeah? Matthias, what's the domain? What do you mean, like left side or right side? Start with left and go to the right. So 1, 2, 6. Okay. And then those are both, Nathan, Dylan, those are both dots. So we're going to use square brackets for both of those. And then what's the range? -1, good. All right. Okay. All right. Do we have more of these? Or are we? There's 4 more. Okay.
There's actually 9. It's actually, it looks like a tracking them.
Riley? What's the domain of this? How far to the left does the graph go? But it's got an arrow there. So yeah, negative infinity that way. Infinity this way. And then the same thing is true of the range because it goes down forever because of the arrow and up forever because of the arrow. So that's also going to be negative infinity to infinity. Riley, is this graph increasing or decreasing? Good deal. Is it possible? Is learning happening? You guys seem to be answering these questions more quickly. Dylan, what's the domain? -5 to unlimited. Good. And what's the range? Nice. Increasing or decreasing? Jaren? Domain? Shh. Okay, we got to go from left to right, so other way around. Negative infinity to 5. The range? No, because I'm looking at the y values, and the y value of this point isn't 5. -1. Right. So negative infinity to -1. Increasing or decreasing? We always go left to right. So if I start over here and I walk on the graph, am I walking up or am I walking down? So increasing. Okay, McKenna, how about the domain? Yeah, yeah, absolutely. So how far to the left will this graph move if we like extend it forever? What's that? Yeah, I think it goes forever that way because it's still moving that way a little bit. So, and then this way it goes forever also, right? How about the range? What's the lowest part of the graph? What? I just can't hear you. Shh, 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 shh. You know, it's kind of hard to tell, isn't it? Is it going to keep going down like a little bit, or does it level off at, I don't know, let's say it levels off. So let's go 0, and then how high will it go? Infinity. Kind of? Okay. Increasing or decreasing? Decreasing. Okay. Next ones, now we get to find some formulas. Hello. So it's all formulas now? Okay. Okay, Weston, what do you got for a formula here? Yes, good. Oh, sorry, 1x plus 2, because it's going up by 2 each time. Okay, so that's the explicit formula. The recursive formula is, shh, shh, boys. What's that? Yeah, so the recursive formula is to get the next one, you take the one before it and add 2. Okay? That's the recursive formula, yeah. I feel like we did these before. Like, well, whatever. No, the reason why it's 1x is because if you walk this back to where n is 0, then that one would be 1. Okay? Okay, Luis, give me an explicit and a recursive formula for number 11. Well, what would you be starting at if you went back to 0 here? What you have, so, right, so this one would be, which is 1, okay? So you're starting at 1, so y equals 1 times, what are you doing to the numbers each time? Multiplying by 2, so 2 to the x, okay? And then do you know how to write the recursive? Times 2, yeah, okay. I have cap erasers. What do you? Okay. Oh, I don't have. No, I got it. So what you really want is that, yeah. All right, next one. Matthew. Matthew. What's the explicit formula? Okay, so we know it's going to be y equals negative 4x. Where did it start, though? So if I go down, this is going to be 5, 4, 3, 2, 1, 0. So if I go down one step, I'm going 27. If I go another step, I'm at, and then 43, and then 47. So it'd be y equals negative 4x plus 47. Is that what you're going to say, McKenna? Okay. And then do you know how to write the recursive formula for that? No, what are you doing each time? Minus 4.
All the ones that say -1 here going back to 0.
You're going, no, you're just going back to the one before it. Okay. Can anybody tell me how Matthew could have gotten 47 without us going through that whole process of adding 4 and adding? How many times did we end up adding 4? 6, because we were starting at 6. So instead of going plus 4, plus 4, plus 4, plus 4, you could just go 6 times 4 is 24, and 23 plus 24 is 47. Okay, so that just saves you a little bit of work there. All right. All right, Nathan. Good start. What is our starting value here at 0? No, I want the starting this value. What's happening to these numbers? What's the pattern? Right. So it's not, you were thinking adding 2, so you subtracted 2. Okay, but it's really multiplying by 3, so to get this one you would divide by 3. So that's going to be 1/3. So it's y equals 1/3 times, because this is a geometric one. What are you multiplying by each time? Okay, so 1/3 times 3 to the x. Okay, so for the recursive, you say f of n minus 1 times 3, because you're multiplying by 3 each time. Good. So what's a way that you can say dividing by 2 that's actually multiplying by something? McKenna. How can you change dividing by 2 into multiplication? Dividing by 2 and multiplying by 2 are not the same thing. I want to know what's the same as. Okay, let's figure out the starting point first. So 2, 1, 0. What would this number be? 16. What's this one? 32. And so our starting number is 64. Okay, so this is going to be y equals 64 times. What's the same class as dividing by 2? What's a way that you can do that with multiplication? Multiply by 1/2. So 64 times 1/2 to the x. Multiplying by 1/2, dividing by 2, same thing. Okay? Okay, so then the recursive formula is take the one before it and multiply by 1/2. All right. Yeah. Okay, Weston. We got some work to do here. Okay, but here's what we have to be careful of. Nathan, Dylan, we're adding 6 each time over here, right? But what are we adding? Oh, okay, good. So if we're adding 6 every time we add 3, how much do we add every time we add 1? So this is going up by 6. This is going up by 3. No, it's 6 divided by 3, which would be 2. Is that what you're going to say? Okay, I just wanted Weston to have a chance at it. So that's y equals 2x. So then if I walk this backwards, if I go 3, 0, so if I'm going that way, instead of adding 6, I need to subtract 6. So my value at 3 would be 1, because and then my value at 0 would be, if I subtract 6 again, -5. So my explicit formula is y equals 2 times x minus 5. Okay? And then in the recursive world, what are you doing every time? To get the next one, what are you doing? What'd you say? No, I'm going adding, not adding 6. I'm adding 6 every time I make a jump of 3. Right, adding 2, yeah. Because I always want to know what am I doing each time, not every 3 times. All right, and then the last handful here. What did we go down by here from 40 to 32? We went down by 8. What did we go up by here? 2. So that means that overall we went down by 4 each time. Does that check out with this? What did we go down by from 32 to 16? 16. And what did we go up by over here? 4. Good. So that means that negative 16 divided by 4 is also negative 4. So our explicit formula is negative 4x. What is going to be the value of the function when n equals 0? If I went down 8 here when I went up 2, what would I go going this way if I go down 2? Anybody know? Matthew, we'll take your input now. What is this function going to equal when n is 0? Yeah. I don't think so. Am I doing it wrong? I feel like it's 48. Because then that would be down 8 again here when you go up 2. And negative 8 divided by 2 is still negative 4. Because, well, they jumped here. Instead of going up by 2s, they all of a sudden went up by 4s. So that's why the minus 8 doubled to be minus 16. What are you saying? Oh, I see what you're saying. Oh, yeah. So if you decided that this was not linear, then you could make a more complicated thing that would still fit the pattern. Yeah, you're right. But I'm going to go with this because it's a little bit easier. Okay. So then the recursive is to get the next one, you take the one before it and you subtract 4. Okay, what's the pattern on number 17? It's dividing by 4 every time. So it's going to be y equals something times 4 to the x, because you're multiplying, I'm sorry, you're dividing by 4, so it's times 1/4. And then you just have to find this starting number again. So the next one up would be 4 times 16, which is 64. And then $256. So 256 times 1/4 to the x. And then the recursive is take the one before it and multiply by 1/4. All right, last one. This is another tricky one because over here the change is not consistent. Here it's up by 3, here it's up by 6. What did it go up by when we went up by 3? By 5, and then here it went up by 10. So if I go this change divided by this change, the slope is 5/3. And then we would have to walk that all the way back to figure out what it is at 0. How many times would we be adding? I guess if we go the other way, we're subtracting. How many times would we subtract 5/3 to get to 0? We're starting at 17, so to get to 0, we're going to have to take 17 steps back. So 5 is what we're starting at, and then we would subtract 5/3 17 times. What is that? You got to... I got negative 23 1/3. Oh. Okay, so what are we doing to get the next one each time? What? What are we adding? Plus 5/3. This divided by this divided by that. All right?